Up to now in this course, we've been looking at results that are proved without the help of one of the most fundamental tools in the subject, which is discrete Fourier analysis. But that changes from this lecture onwards because, well, we're going to prove some theorems that basically need Fourier analysis for their proofs. But once we've seen a bit of Fourier analysis, it will provide you with, if you want to go on and solve problems in additive combinatorics, it will provide you with basically a sort of big expansion in your mathematical proving power. It just provides a tool that enables you to do a lot of things that would be either very hard or even impossible otherwise. And I'll try to explain why that is and what sorts of problems it's useful for in due course, because we've seen some quite interesting results proved without Fourier analysis. So what is it that makes a result suitable for use of Fourier analysis? So we'll discuss that. But first we need a few preliminaries. So let us get going. So before I start, I want to say just a little bit, which may be familiar material to some people watching this, a little bit about characters on finite abelian groups. So let's take, I need a thicker pen. Let's take G to be a finite abelian group. Then a character on G is a homomorphism. Well, let's just say I'll call it a multiplicative homomorphism to C, by which I mean i.e. a homomorphism to the group C minus 0 with multiplication, normal multiplication over the complex numbers. And because every element of a finite abelian group has finite order, and because the modulus of a product is a product of the moduli, we see immediately that if chi is a character, then chi of x modulus equals 1 for every x in G. So really we can think of it as a homomorphism not to this big group but to the smaller group, which I could denote by T, which is the group of complex numbers of modulus 1. Let's make a couple of very trivial remarks. So if chi1 and chi2 are, well, actually, trivial but important, I suppose I should say, are characters, then so is chi1, chi2, where by that I mean pointwise multiplication. So chi1, chi2 of x equals chi1 of x times chi2 of x. It's simple to check that that is also a character. And so is, if chi is a character, then so is chi to the minus 1, where I mean by that the sort of pointwise inverse, which is the same thing since we're inside the complex numbers of modulus 1. It's the same thing as the complex conjugate of chi. Again, the pointwise complex conjugate. So chi bar of x is chi of x all bar. And those facts, together with the fact that also the function chi naught, which sends x identically to 1, is a character. It's the trivial homomorphism. And, well, these little observations important in themselves, but in particular they show that the characters form themselves a group, and we can see straight from this definition that it's abelian. And we'll see a bit more about that in a moment, but before I go any further, let's prove a lemma that's going to tell us that characters are orthogonal to each other, actually. But before that, I want a definition. So I want to say precisely what I mean by orthogonal. So if f and g map our group to the complex numbers, we're going to define an inner product by, I didn't express that sentence terribly, but I really should say, define an inner product by the following blah blah blah. If f and g are those functions, then their inner product is the following. It is the average, I think we've had this in the course, if not I'll say a little bit about it in a moment, x of f of x g of x bar. So perhaps I'll just, I think we've had this notation already, but just in case, where ex of some function f of x means g to the minus 1 times the sum of all x f of x, when f is a function defined on g. And in general, if f is defined on some set capital X, this means it would be, I'd replace that g by capital X. Yes, I did have that in some discussions about bipartite graphs, that notation, but it's going to be extremely useful to us. So lemma so G is still a finite abelian group, so if chi1 and chi2 are distinct characters, then chi1, chi2 equals 0. A little comment. So you might have expected me to define inner product, instead of writing this average, to have a sum over x. I'm going to discuss in a moment a bit about when sometimes we do define inner products with sums. I'll say a bit about it in a moment, about when we do and when we don't. But first let's prove this lemma. So let chi be a non-trivial character. So by non-trivial, I mean it's not the identity character, it's not the one that sends everything to 1. And let u in G be such that, since it's not identically 1, we can find a u such that chi of u does not equal 1. And what I'm about to do is basically the trick one uses for summing GPs, but in a slightly generalized form. So then the average over all x of chi of x is the same as the average over all x of chi of u of x, because the map x maps to u of x is a bijection, because u is just an element of, perhaps I should say u plus x, since we're in an abelian group. Slightly clearer to use additive notation, or is it? I don't know. But anyway, chi of u plus x, because chi is a character, equals chi of u times chi of x. So we can take out a chi of u. And now we see that this thing here equals itself times something that is not equal to 1. And so that implies that this average here equals 0, so since chi1 doesn't equal chi2, we get that chi1 chi2 bar is a non-trivial character. The result follows, and if you don't immediately see why I said that, just notice that the inner product chi1 chi2 is the average over x of chi1x chi2 bar of x. That's exactly the average of this thing, and this was a non-trivial character, and this tells us therefore that the average is 0. So that's a very useful fact, orthogonality of the characters. So that tells us that since the space of functions from G to C has dimension G, sorry, size of G, there are at most, and the characters are orthogonal, there are at most size of G characters. And that's because orthogonal functions are independent, a fact that I assume that you know. A bit less trivial is that they actually span the space of functions. In other words, there are exactly the size of G characters, and I'm not going to prove that in full, but I'm going to prove it assuming the structure theorem for finite abelian groups. So that structure theorem tells us that we can write, let's just write Zn equals, I'm going to write that as useful notation for the cyclic group, or the group of integers mod n, and that's just a particular realization of the cyclic group of order n. So I'm going to assume that G is Zn1 cross Zn2 cross Znr for some n1 up to nr. Under that assumption, which I'll call this a lemma, so if G is this thing here, then the characters on G span G. Span the space of functions from G to C. So what I'm actually going to do is associate with every element of this group here a character. In fact, I'm going to prove that G is actually isomorphic to the group of characters. Afterwards I'll comment on what the significance of that fact is. But so let U in, so U equals U1 up to UR be an element of G. So obviously UI belongs to Zni. And a bit of notation I meant to introduce, but I'll write it up here because it seems out of place within the proof. Some notation that is very useful is to write E of alpha for e to the 2 pi I times alpha. That is very standard notation in analytic number theory, and occasionally it's useful in additive combinatorics as well. Then the function chi of u, which takes an element x of G, so x equals x1 up to xr, to the product I equals 1 to r of E of U I xi over ni, and I'm going to have to comment on this in a moment, is easily checked, and I think this really is genuinely easy, I'm not cheating, to be a character. Maybe I can just say out loud why it's a character. So if x equals y plus z or something, then each xi will be yi plus zi. E of that lot will split up as a product of e ui yi over ni times e of ui zi over ni, and then that whole product then splits into a product of two big products, and we get that chi of u is indeed a character. But one thing I need to be a bit clear about is this looks a bit strange, this expression here, because ui and xi are elements of zni. That's integers mod ni, and you can't sort of divide an integer mod ni by ni. But you sort of can. If you take the integers mod ni and apply that horrible map iota from the previous video, in other words, you just regard them as elements of z, then you can divide by ni, because now they're elements of z, so I divide by ni, I get some funny rational number, and I can take e of that rational number. And the one thing that you need to check if you're feeling a bit squeamish about that is that if I were to choose different residues instead of ui and xi mod ni, I would get the same answer, but I would, because I'll just add some multiple of ni if I replace xi and ui by different residues mod ni. Then when I divide by ni, that means I'm adding some multiple of 1, but the function e here is periodic with period 1, so adding 1 doesn't matter. So we've got some unpleasant, not well-defined thing composed with something that collapses numbers together that if they differ by an integer, and then so the composition of this multi-valued function with this collapsing function gives us something that's well-defined. So I could say easily checked to be both well-defined and a character. And different u's give different characters. And so that's the end of the proof of that, but sort of observe also that the map u to chi of u is an isomorphism. And there's something I haven't said. So it's an isomorphism from G to what? Well, to the group of characters that we saw was a group. But I forgot to define it, or give notation for it. So we write G hat for the group of characters on G. And this is called the dual group. And sometimes it's also called the Pontryagin dual. Of G. Now I said that I was going to make a little remark about the isomorphism, and the remark is that this isomorphism here is not a natural isomorphism. And the reason it's not, so this is a category theory concept, a concept of a natural isomorphism. I'm not going to try and explain precisely what a natural isomorphism is, partly because I might make a hash of it myself because I'm not at all a category theorist. But I can at least explain why this is not a natural homomorphism. It's because when you've got an abelian group, yes, you can decompose it as a product of cyclic groups, but not in a unique way. There's not some canonical way of writing G as a product of cyclic groups, or to put it another way, that you've got plenty of automorphisms of G and non-trivial automorphisms. And if you decompose G in a different way and then define the automorphism according to what the sort of process I've just done, you'll find that you get a different isomorphism. So the the process of sort of defining isomorphism in some sense doesn't commute with the process of deciding how you're going to split G up as a product of cyclic groups. And so that's why we'd say that the map is not a natural map. And for that reason, it's not necessarily a particularly useful fact that those two things are isomorphic. But it's kind of useful from the point of view of just notation and that kind of thing. When we're talking about a specific group, it's quite nice to be able to just identify elements of the dual group with elements of the group. Now, let me just say a little bit more about norms and inner products. So I've defined an inner product on functions defined on G by, let's just recap. So inner product of f and G was the average of fx times gx bar. But if I have two functions, which I'm going to put hats on, are functions on the dual group of G, we define the inner product in a different way. We define it in the old-fashioned way with sums, sum of all chi, sum over all characters. Yes, that's okay. F hat of chi. I thought I might be assuming something that I hadn't yet talked about, but I'm not actually, because these are just arbitrary functions from G hat to C. And so their arguments will be characters, so I'm summing over all characters here. Now, the reason that we like to have averages for the original group and characters, and sums for the dual group, is that later on we're going to be taking Fourier transforms, and the Fourier transform of a function on a group is a function defined on the dual group. And what we like is that the quantities that we look at typically have order of magnitude 1. And the sorts of functions that we're going to be looking at on the group will tend to be functions whose values are sort of between 0 and 1, things like that. And so that means that when you take the pointwise product and average it, you'll get something that's of order 1, also between 0 and 1. Whereas when we take the Fourier transform, we tend to get a function that is sort of big at a few values and small outside those few values, and then somehow taking sums is more appropriate. And it's more likely to lead to a quantity that is of order of magnitude 1. And it's rather nice with these sorts of normalizations. If the quantities of interest tend to have norm 1, then it's a good way of catching mistakes. Sometimes you find that you've generated some quantity that is sort of the size of at least root G or something, the root of the size of G, and then you think, well, that's a bit funny. Where did I go wrong? Well, in fact, actually, in a way, that doesn't happen very often, because somehow the discipline of using these concepts means that those mistakes are less likely to happen. Anyway, so now we've got those, we've got these inner products. Let's just say I've got X, a finite set. I'll define LP of X. It's a set of functions f from x to c. Sometimes I might want real valued functions, in which case I might say LPXR or the real LPX or something. And the norm of f is going to be defined using averages. But otherwise it's the familiar formula for the LP norm. But I will also have the little LP of x, and there it's the same, it's functions from x to c, but this time fp is the sum. And so in particular, f2 squared equals ff, so we get the L2 norm. Either if we're working in capital L2 here, in which case we've got this, or we're working in little l2, in which case we've got sums on both sides of this definition. I should say that the L infinity norm, which is just the maximum, that's the same whichever way you go. So maximum x f of x. Now, I think I may have done enough to worried. I feel as though I've forgotten something important, but I can't think of it. So I'm going to define the Fourier transform now. And if I suddenly remember, I'll have to stop and insert some extra remarks. So if f maps G to C, this is a definition coming up, the Fourier transform, or the discrete Fourier transform of f is the function f hat from the dual group G hat to C, given by the formula f hat of chi equals the average over all x of f of x chi of x bar, which is nothing other than the inner product of f with chi. F hat of chi is called the Fourier coefficient of f at chi, or the Fourier coefficient of chi, when f is clear from the context. So we notice that the characters chi form an orthonormal basis, and so when you want to expand a function in terms of an orthonormal basis, this is exactly what you do. You take the inner product of the function with each term of the orthonormal basis, each element of the orthonormal basis, and that gives you the coefficient of that term. So it will come as no surprise that we have the formula f of x equals the sum over all chi of so the Fourier coefficient of f at chi, which is the coefficient of f when you expand in terms of this orthonormal basis, times chi of x. Now that's not quite a proof, what I said. Those remarks were, it can be converted into a proof, but you've got to be a bit careful about the normalization, and I think it pretty much was a proof that these two things are proportional to each other, but that they're exactly equal. You have to be a little bit careful and check. I'm actually going to, in the next video, give, instead of trying to argue abstractly, I'll just give a completely direct computation that proves that this thing reduces to this. But I'll make another remark in the more abstract sense. Since we've got an orthonormal basis, we know that the L2 norm of f is in fact calculated by summing the squares of the coefficients. So let me put a square there. So we get the sum over all chi of f hat chi. Those are the coefficients of the chi's, and the chi's were an orthonormal basis. And that's just the same as f2 squared. And again, maybe I glossed over whether the normalization really works out, and again I will give a proper proof in the next video. But I will mention as a third fact, which you can get from this using polarization, but actually we'll do it the other way around. We'll prove this fact and then deduce this, which is that if f and g are two functions, then the inner product of f and g is equal to the inner product of f hat and g hat. And this is known as Parseval's identity, or sometimes as the Plancherel theorem. And again, one of the nice aspects of choosing this averages and sums is that we don't have some sort of normalizing factor like mod g here. It's just an absolutely straight equality. So those are two very basic properties of the Fourier transform, and there is a third one which I will talk about next time. So today, this video was just basically a whole lot of definitions and some rather basic facts. But next time will be fewer definitions, more basic facts, and then the video after that will be showing you how to prove some quite powerful results using just these. I'm giving, it's a rather short crash course in discrete Fourier analysis. Not much to take in, simple results, but once you've got the tools in place, you can do some pretty incredible things with them. So that's it for this video.